Okay, so in a previous video, we talked about spectroscopy. And we talked about the main uses of mass spec, IR, and proton NMR. The purpose of this video is to talk more about mass spec. Okay? So let me again say that suppose we have a structure. If the main purpose of mass spec is to identify the molecular weight from which we can oftentimes get the molecular formula, if that's the main purpose, let's consider a couple compounds that have the same functional groups and the same connectedness but different molecular weights. And my guess is that some of you are watching this without that being eminently obvious, because it's an introductory class, right? So you may be thinking, how can I have the same functional groups and the same connectivity but different molecular formulas? And so here's an example. I gave an example in the previous video, but here's another one, I think a better one. What about cyclopentane, cyclohexane, and cycloheptane, right? You can see that these are all CH2, 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 just rings of CH2s, right? So they have exactly the same functional groups in them, namely no functional groups at all. I guess we would call these alkanes. If we were talking about functional groups, that's oftentimes what we would say. It's really the absence of all functional groups, alkanes. So they have the same functional groups in them. And they have the same connectivity, right? They're all CH2s connected to CH2s, all of them. But they have different molecular weights. So, in order to appreciate that even better, let's look at the IR spectra, right? The IR spectra of all three of these guys. And we'll see that they look pretty much the same. Okay, so first of all, here's the IR spectrum for cyclopentane. All right, now don't forget that the fingerprint region starts at 1500, so we cover up 1500. Everything below that is just stuff that we don't, in a class of this scope, investigate. Okay, so you have a big peak right there at 3000 and a couple minor peaks. All right, that's cyclopentane. Let's look at cyclohexane. Cover up 1500. So again, a big peak around 3000. A couple minor peaks. All right, and then finally cycloheptane. Cover 1500. All right, a big peak at 3000, and not much else. So again, let's look at those one more time. Cyclopentane, cyclohexane, and cycloheptane, right? That is pentane, hexane, and heptane. All right. So we know that that IR is not. That's meant to identify differences in functional groups, right? And these don't have differences in functional groups, but they are different by their molecular weight. Okay. So you can see that if you're looking at those compounds, these three compounds right here, the most important difference is molecular weight. So let's look at the molecular weights. All right. I did forget to mention that the peak upfield, the peak that's most upfield is the biggest particle that we can expect from this thing as it breaks apart. And I realize I haven't even told you what mass spec is. I'm hoping you'll get that from the book. I'm dealing with you in parts that are more difficult. So let's think about this. What's the molecular weight of cyclopentane? It's going to be 5 times 10, no, times 12, plus 10 times 1, which is equal to 70. Right, because there's 5 carbons. 5 carbons plus 10 hydrogens. Right, what about cyclohexane? It's going to be 6 times 12 plus 12 times 1, which is going to be 7284. Okay, and then cycloheptane, 7 times 12 plus 14 times 1. Right? Can you see that there are 7 carbons in here, and each one of them has 2 hydrogens on it? That's why we're getting those. 7 times 12 is 84, plus 14 is 98. Okay. So they should have different mass spectra. Let's look first of all at the cyclopentane one, just to give a visual. Okay, cyclopentane, there's a peak at 70,